Now, since we have learned the basics of gravitational potential energy, let us understand the concept better by doing a couple of problems on this topic. So here is the first problem for us in this lecture. It says that three particles of mass m each are placed at the corners of an equilateral triangle. Find the work done in increasing the length of the sides of the triangle from A to 2A. As we read the question, we can visualize it with the help of figures. Initially, the particles were placed at the corners of equilateral triangle of side length A. So let me call this triangle as ABC for convenience, and each side has a length of A, and there are three particles of mass m each placed at the corners A, B and C. I'm writing here as well, the particles have mass m each. That was the initial situation. And finally, the particles are separated by an external force so that they are now placed at the corners of an equilateral triangle of sides length twice A. So here is the new triangle, that is DEF, also equilateral of side length twice A, and the particles are placed now at the corners D, E and F. Okay, the masses of the particles are m each as before, but the separation between them has gone up because of an external force doing work on this system. So that is the final situation. Well, initially, as you are aware of this relevant formula we have taught you some time back, that for a two-particle system of masses m1 and m2 separated by a distance small r, the potential energy for the two-particle system is given by minus capital G, gravitational constant, into the product of the masses of the particles divided by the separation between them. The minus sign is sitting because we conveniently assume that when there are infinite separation, these two particles, the potential energy of the system is taken to be zero. Now, we can apply this formula for the three pairs of particles possible for this three-particle system. We shall consider particles at A and B first as a pair, find the energy, then find the energy for the pair at B and C, and then at C and A. We have done it before, just a short time before. So, let us write down initially the potential energy of the system of these three particles. I'm writing it U system initial. Let us calculate that for the particles at A and B, both having mass of m each, separation is A. So, for the first pair, it's minus G into m, both having the same mass. I am having an I on the equation above and just following it blindly here. Divided by the separation is just A. Go to the next pair of particles, that is particles at B and C. Once again the same term, minus G into m by A only. So I'm getting it actually twice. Minus G into m divided by A, and then again for the pair of particles at C and A, we get the same term, that is minus G m into m divided by A. You add them up. This is a simple arithmetic addition because potential energy is a scalar quantity, and you are getting it to be minus 3 G m square by A. Is not it? This is the initial potential energy for the three-particle system placed at the corners of an equilateral triangle of side length A each. Let us come to the final situation, which is depicted in my second figure here, and proceeding in the same manner, that is taking up a pair of particles at a time and using this formula again and again for a two-particle system, we could write down that the system's final potential energy is coming out to be minus, once again consider the particle pair at D and E, both having mass of m, but separation this time is twice a. So I'm getting it to be minus g into mass of the two particles multiplied divided by separation is twice a. Look at the next pair particles at E and F, the same expression, minus g into m square by twice a, and the particle pair at F and D, the same thing, minus g into m by twice a. So I'm getting this term thrice for three pairs of particles possible, and I'm just multiplying by 3 to save some time and space, and I'm getting this coming out to be minus 3 capital G into m square by twice a. Tell me, is it an increase or decrease in potential energy? It is common sense that as the separation between them has gone up from A to 2A, the absolute value of system's potential energy actually has gone down. Therefore, the change in potential energy for the system, that is the final value of the potential energy minus initial value of potential energy, is coming out to be minus 3gm square divided by twice a minus the value of initial potential energy minus of minus. Remain careful about the signs by a, and when you make this calculation, this is coming out to be actually plus, you can check it, 3gm square by twice a. So in taking the particles from a separation of a each to a separation of twice a, there is an increase in potential energy of 3gm square by twice. And once you are here, you remember the work energy theorem for a non-isolated system of particles, as we taught you under the chapter of work, energy and power, which says that the work done by external force on a system of particles is equal to the change in its energy. In this case, it is change in potential energy only, and therefore the work to be done on the system of particles is same as delta U, and that is coming out to be 3gm square by twice a. And here is the answer of this question. We have found the work to be done externally on the system of particle is 3gm square by 2a, where g is gravitational constant, m is the mass of each particle, and a is the length of the side of an equilateral triangle initially.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.